Thanks for inviting me. So we're going to continue the drumbeat of all plugins that we had the last 2 days with LowFive. But unlike some of the previous ones, the purpose of LowFive is not going to be to reorganize the storage format or to pick a different storage target. The purpose will be to avoid storage altogether. And what I mean by that is, imagine that now you have what we would call an in-situ workflow. Imagine 3 different executables. Producer could be maybe a simulation code, consumer 1 could be some analysis code, consumer 2 is a visualization tool. All 3 of these are parallel MPI programs of different sizes and scales. They're launched at the same time in one run on a supercomputer, and they need to communicate with each other. So we'll call that an in-situ or an HPC workflow. In-situ because they're residing at the same time in one run, and they need to talk to each other over a data transport layer, which is going to now be LowFive. And that will be using MPI, direct communication, rather than through the file system. And not surprisingly, we'll do this as a Vol plugin in HDF5, that's why we're here. And this work appeared in IPDPS earlier this year. You can search for the paper of the same title to find out. So we have a few decisions to make in implementing this. One is, what data model do we use? I don't have to convince anybody here that HDF5 is the right choice for that. We can do this data transport in a couple of different ways. One way is to create a third-party kind of staging area. Some tools like data spaces do that mechanism. The other way is to just directly send MPI messages from MPI ranks of one code to MPI ranks of another code. That's what we do in LowFive. Another choice we have to make is where to intercept IO calls, because that's what we're doing, right? We're intercepting IO and redirecting it, and there are different places in the software stack to do that. And the design of the software is modular. LowFive is a standalone library. It's used as a layer inside of other workflow systems, as opposed to being part of some larger system that you have to buy into in order to use it. So we'll talk about some of those things in a little more detail. One is this idea of a direct transport mechanism versus a staging area. Logically, it looks like the diagram on the left. LowFive is this kind of separate thing. It looks like it's in between producer and consumers. And in fact, it could be implemented that way. As I said, other tools implement staging areas this way. But in fact, the way it's implemented is the diagram on the right, where each MPI rank of each code has a copy of LowFive that maintains the locally distributed parts of the data that rank maintains. And each of those copies of LowFive talk to each other over MPI in a direct MPI send and receive kind of a way. Where to intercept IO calls, burst buffers and things like that, perhaps intercept them at the POSIX level. That's too low of a level for us. I also probably don't need to convince you of that. There's no metadata attached with that. There's just byte offsets and lengths. That doesn't work for a workflow system where we need data set names, data types, data spaces, and so on. The opposite extreme is to rewrite the data model at a high level in a completely different way. Conduit, Bredela, other tools, Adios, perhaps you could say do this. That requires changing the user code, though, then to adopt that data model instead of what they may have natively done. Of course, for us, the middle ground is to use HDF5, requiring no changes to the codes as long as they're using HDF5 or something that has an HDF5 backend. And HDF5 gives us all the metadata that we need in order to transport data efficiently through our workflow system. And it gives us the vol mechanism in order to do that conveniently as developers, right? So the software stack looks like this. We can see HDF5 kind of in the upper middle. Below that is LowFive as a vol plugin. Underneath that, we're using our DIY block parallelism programming model. That's basically our layer on top of MPI that we use to do data redistribution and data movement. below that is MPI. On top of that are either HDF5 native API or NetCDF4 or High5 or H5Py or Scorpio or Amrex or blah, blah, blah. Anything that has an HDF5 backend, and on top of that are codes and workflow frameworks. And what we do in LowFive is we build up in memory our own version of your metadata tree, right? As a tree in memory where we build objects for the file, for groups, for data sets, for attributes, for pretty much everything that HDF5 supports. And then we access these objects when it comes time to send data from producer to consumer rank. We manage in here pointers to the data sets, either deep copies or shallow references. That's up to, that's a knob. And as I said, various fields associated with data sets, like their types and data spaces and so on. And this is really what LowFive, this is a central part of what LowFive is our in-memory replica of the HDF5 hierarchy. And one of the key things that we need to address is how to redistribute data from M producer ranks to N consumer ranks, where M doesn't have to equal N. And even if it did, even if those two were the same, there could still be entirely different decompositions. For example, on the left side, the producer has a row-wise decomposition of a 2D space. On the right side, the consumer has a column-wise decomposition. And neither one knows about the other. These are independent codes written independently, and they just happen to be launched at the same time, but they know nothing about each other, right? And now the question is, how do we send only the intersection of rank 0 on the producer to rank 1 to rank whatever on the consumer, the intersections that logically intersect. And we talk about this in the paper, how we actually pull this off. I won't have time today to explain it, so that's your teaser to go read the paper, how that's done, but that actually works correctly. And now I'll go into some synthetic and real evaluation results of how this works in practice. So for synthetic benchmarks, we set up a number of different scenarios. We do one producer and one consumer in a workflow of some total number of ranks, MPI ranks that are on the left side of the table, divided it by a ratio of 3 to 1 in producer ranks to consumer ranks. So M does not equal N, right? In fact, they're 3 to 1. And on each of those, we put 1 million grid points in one data set and 1 million particles in a second data set per producer rank, and we send them to the consumer ranks. And that's the benchmark test, how long it takes to do that data transfer. There's no compute, it's just pure data transfer over MPI, okay? And then we do it in a variety of different ways. So in the left on the green, we can use LowFive in memory mode, the way we intend it to be used in MPI, but we can also use file mode where we actually do create and write and read a physical file. That's another switch in LowFive. So we'll compare file and memory modes in LowFive. We'll compare those with pure HDF5 without LowFive, just to make sure that we don't incur too much overhead. We'll compare that with pure MPI, to again make sure that we don't incur too much overhead in memory mode of LowFive. And we'll compare that with one other tool, data spaces. Okay, so that's what's coming up. And the first test is LowFive memory mode in green versus LowFive file mode in white. Time is on the vertical, lower is better. And this is a weak scaling test. The data size grows with the number of ranks, which means that ideally it would be flat, right? Now the memory mode isn't quite flat because there's no compute, there's just communication. You'll never get 100% weak scaling efficiency. We get something a little bit less, it ramps up a little bit, but nonetheless, it's much faster than file mode. We didn't do anything to tune the file mode here. This is just out of the box on Theta at Argonne, whatever the file system gave us. we didn't care. You could tune this, you could bring that time down, I'm sure, but of course, memory mode and MPI will still be faster than file. That's why we do in situ, after all. This is just a baseline to, you know, say everything is sane so far. And the next test will be to compare HDF5 file mode versus pure HDF5, LowFive file mode versus pure HDF5 without any LowFive, just to make sure that we don't have too much overhead. Those curves are pretty close to each other. That's good. We're happy with that. The next test is to compare LowFive memory mode with a handwritten MPI code that does all of the same transfers. We check that all of the data are received correctly. By the way, we encode values into the data points, and we assure that they are correct, and we get the same result. The LowFive actually is a little faster in most of these cases than the handwritten code. That's because I wrote the handwritten code. And I didn't do a whole lot, I didn't spend a lot of time optimizing it. So LowFive actually does a good job using HDF5's iterators and things like that. It groups together contiguous runs of data and like that. But I didn't bother to do in the handwritten code. You could think of the handwritten one as sort of an average domain scientist written code. Not the most naive thing, but not the most optimized either. But the point is that we don't really incur any overhead in LowFive in memory mode either. That's fine. And the last test is now a slightly larger test. We made all of the data sizes a factor of 10 larger than before. So one of the reviewers in the IPDPS process said, what about larger data? Your data size is a little too small. So we added one more result where we scaled everything up by a factor of 10. And here we include memory mode in LowFive and MPI. Again, white in LowFive and magenta in MPI. Those again seem to track pretty well. So the MPI versus memory is pretty close as it was before. And now we include in green a data spaces test, and data spaces is a little bit faster than we are, about 20% at scale. And that's okay for us. Couple of things. One is data spaces uses a third staging area that we don't. So it uses more resources than we do, right? It has a dedicated area where it stages data. It does that asynchronously, whereas we are fairly synchronous. And second, it has a very limited data model. It's basically n-dimensional arrays, whereas LowFive supports a full HDF5 complex data model. It's not necessarily being exercised here, but we do support that. And for that, we trade a little bit of performance, and that's all right. I think that's a fair trade-off. Next, we tested this in an actual science application. Nix is a cosmology code. Reber is an analysis code that does topological analysis. It constructs merge trees to search for halos in the cosmos. And the takeaways here are in these two right-hand columns. When Nix writes using native HDF5, then LowFive is up to 320 times faster than Nix writing HDF5. We're using memory mode, they're using files. That's not surprising, just again proving that this works in real applications. And then Nix is using Amrex, by the way, underneath the hood. They have a plot files format that's faster than HDF5. It's some sort of a home rolled subfiling thing, if I understand it correctly. And so it's faster, but we're still 20 times faster than that. The important thing here is, one, it works in real science, but two, no changes were made to either code to use LowFive because Amrex uses HDF5, and so we're able to catch that. Reber does as well. So 0 code changes for the speed ups. That's perfectly good result. And so in conclusion, LowFive is a data transport layer for HPC workflows. Vol plugin using HDF5 allows us to bypass storage, send data over MPI, redistributes data between different numbers of ranks and different decompositions, and is a standalone software library that other workflows can build on. We're building other workflows on top of that now. That's some of our next steps. We're also implementing the last few features that we haven't implemented yet, namely data types in HDF5. are a bit of a sticky point for us, working on some flow control. And I just want to close with an example of 3 different software stacks that use this today. On the left is Climate and E3SM. There, they use the Scorpio IO library that wraps netcdf4, which then translates to HDF5, which means we can catch that with LowFive. On top of that, we build workflow tools like Henson and Wilkins. Those are ours at the top. In the middle is the Nix example that I just showed you using Amrex and HDF5, and on the right is an AI example using Keras and H5Py, which again, we catch through HDF5. So all of those things work today. And with that, I'm happy to take questions. Thanks.
Thank you. Questions?
Thanks for the talk. Maybe this is a bit of an obvious question. I understand the producers are just using the HDF5 interface. Could you explain a little bit more about how you're connecting the consumers?
They're just using HDF5 dataset read, HDF5 file open, HDF5 dataset read. Both producers and consumers think they're writing and reading HDF5 files, and in fact, their calls are being intercepted by us.
So they're opening the same file, but with different options to the Vol connectors.
I think the options in the Vol connector are the same as well. I'm not sure I understand that part. They're certainly both opening the same. Oh, well, sure, yeah, but other than that, yeah. Thanks. Yeah.
Thanks.
I'm assuming the 2 applications, the producer and the consumer, are developed differently, right?
The 2 applications are what differently?
Developed differently.
Developed differently, absolutely.
And when you run, you have certain assumptions that, let's say the producer is running half hour before the consumer started. Do you have anything that detects how much you need to stage?
So what we actually launch both of those tasks or an entire workflow of multiple such tasks all at once, not a half hour before or something. In MPMD mode, basically the workflow system that's on top of LowFive launches in MPMD all of those executables at the same time.
So let's say I submit one, then the workflow environment can detect that the better coupled to be launched or something like that.
We have, like the workflow system has a configuration file where you give the names of the codes and how many ranks you'll assign to each of them and things like that. Okay. And then you'll launch that job and the workflow will go and create a job submission that couples those things in MPMD mode. It will form communicators for each one and intercoms between them that LowFive will then use for the communication.
Okay, that's the question.
So, but those things are all up and running at the same time, and they're basically blocking, waiting for each other synchronously.
Okay.
Right, yeah. I didn't give a lot of that context, but that's the workflow system on top of it, but it's important to understand that as well. Thanks for the question.
Other questions?
One quick question about the communicators and the connections. Are you just using MPI send receive, or are you using any MPI put get kind of thing?
I send and I receive, but okay. That's all point to point. Yeah, non-blocking point to point.
Have you ever considered
we have, but we're using DIY underneath, which is our library, and that is implemented. We put quite a lot of work into DIY, and we found good ways to implement even reductions and things like that out of trees of point-to-point communications that then we have more control over than MPI collectives. So long story about the whole history of that, but there are reasons why we do all that in point-to-point to have more control over it ourselves.
I had one question about the synthetic benchmarks that you used for sanity check, so to speak. Is that available somewhere in a GitHub repo?
It is actually, yeah.
Great.
Send me a mail, I can point to
Great,
that.
because I'm looking at Luke, who is currently benchmarking the Hermes system, and I think that would be a great thing to try.
Yeah, happy.
Thanks. Okay, good.
Did you
good.
find it? Yeah, okay.
Good
Great.
thinking.
Yeah, If you need it, just contact me,
Great.
happy to share that. If
Thank
it's
you.
not- If it's not readily available.
Last question. You also have to complete before the consumers start.
Yeah, we use file open and file close as our synchronization, yeah.
Okay, great. Thank you very much.
Thank you.